Okay, so this set of differential equations is another one of those that just becomes way too messy if we try to actually directly solve it. So instead, we're going to ask a computer to do it. And when we ask a computer to draw something like this, what it's doing is Euler's method. If you'll recall, we did this when we talked about slope fields. If we wanted to trace out a solution to a set of differential equations, we had our starting point, we decided what the slope should be, so that picked a direction, and we went a certain distance in that direction. Then we recalculated the slope, went a little bit further, and repeated this process. And if we choose really short distances, the shape that we trace out ends up actually being really good. So that's what the computer is going to do in just a moment. But before we jump into it, let's take a look at what's going on in all of this. So over here, we have the differential equations we wrote down last time. So there we go. So on the left, we have W prime. So this is dW dt. This is the rate of change of the population of worms. And this is going to be equal to AW minus CWR. So again, A, C, B, and K are just going to be constants. And for the purposes of seeing what the shapes of these look like, we're just going to assume that these constants are 1. These constants are going to encompass things like units. So the units, because we're saying these numbers are 1, the units are kind of meaningless. We're probably going to be talking about, let's say, dozens of robins and maybe hundreds of worms, sort of roughly the units we're talking about here. One other thing is that up on this upper right, we have our starting position. So how many worms we start with, how many robins we start with. And we're not actually talking about starting with 1.3 of each because the units are weird. Maybe we're talking about 1.300 worms, etc. So the first question, sorry, my scale got messed up here. There we go. So the first question that we have is saying, all right, what should the slope look like for the population of robins and population of worms? So both of them are going to be starting at 1.3. So both of them are going to have their starting population right here. And the question is, which of these are increasing, which of these are decreasing? And we can figure that out by looking at our differential equation. Our dW dt, so the rate of change of the worms, is, well, A and C are just 1, so this is W minus WR. Similarly, dr dt is negative R plus WR. And if we want to know what's happening or what the slopes of these things are for a particular starting condition, we can just plug in those points. So at our original t equals 0, we're saying we have 1.3 worms and 1.3 robins. So dW dt, the rate of change of our worm count, should be 1.3 minus 1.3 times 1.3. In other words, something negative. Whereas on the flip side, our dr dt is going to be negative 1.3 plus 1.3 times 1.3, which I believe is 1.69. So this ends up being positive 0.39, I believe. In other words, the robin population should be increasing and the worm population should be decreasing. Okay, let's take a look at what the computer says should happen. So if I hit play, hopefully this works. Cool. Okay, so it's starting to draw these solutions to these differential equations. It's starting off that our robin population is increasing and our worm population is decreasing. We can start to see what happens after the worm population decreases too much. The robins are running out of food, so maybe this minus R term is sort of dominating this effect, and the WR is having less of a beneficial effect, and now DRDT ends up being something negative. So I want everyone to take a moment, pause the video, and think about what's going to happen to these curves in the future. So as this system develops, what do we think is going to happen next? We currently have worms on the decline, and we also have the robins on the decline. What's going to happen if this trend continues? So take a moment, pause the video, come up with a conjecture, and then hit play. Okay, I'm pretending that you actually did that. So now we're gonna hit play on the simulation, and we're gonna see what happens longer term. So we'll see that while the robin population is declining, that actually ends up being a good thing for the worms. They're gonna start rebounding as well. And well, when the robin population's low, I'm gonna pause it there for a second. When we're talking about this area of the worm population, so going from their bottom up to here, this actually looks a lot like an exponential growth. And that's because in the DWDT part, because worms is so small, because the robin count is so small, the general effect is that it's an exponential growth with just this W term. As the robins start to rebound as well, that's going to become less true, and we'll see what happens from here. We're going to see that we actually get this cyclic pattern where when the worm population increases, that means the robin population increases, which is going to mean that the worm population decreases, which means the robin population decreases, etc. And so we get this cyclic looking pattern, which ends up being not exactly a sine curve. It looks a lot like one, but the troughs and peaks are slightly different shapes. So it's not technically a sine function, even though it looks like one. But we get this similar looking cyclic pattern, which gives us a glimpse as to how this system might function. So a couple other things that we could do is we could play around with these various variables. We could change what the starting conditions were. If, for example, we started with less worms, well, we can see our worm population's dropping here, but over time, we're still going to get this same type of cyclic pattern. Even if we started with relatively few worms, it might make it so that we get more extreme swings, but we still have a cyclic pattern. If we start off in an extreme case where we have very few worms, that's going to cause these really dramatic swings up and down. And this can be dangerous for actual ecological systems because while maybe you have some high populations, maybe that's a good thing, it's also going to occasionally crater out. And in the real world, if we're actually talking about populations, having 0.02 of something, even if it's 0.02 dozen robins, maybe we're down to like 3 or 4, and we're in danger of something actually dying off. So when we have these crazy swings, that's sort of more of an unstable solution. But if we started off where everything was relatively balanced, so again, the units are weird. We're not actually talking about one worm or one robin, but if we start off with a very balanced number of each, we can actually get a stable, it's called an equilibrium solution. Okay, so the thing that we're going to look at in the next video is another way at looking at this relationship and another way of spotting this particular equilibrium position, as well as visualizing in another way how these cyclic behaviors work with varying starting conditions.